question is, won't cross-validation accuracy be a little different for everybody because of randomization? And the answer is yes, but here's why it's going to be very, very little. As soon as I can get my window to open up. There we go. All right. Remember, we measure sum squared error. So this is the, I'm going to be drawing the error surface now. In other words, the horizontal axis is weights. And by weights, I mean the values for M and B in the linear model. And for the vertical axis, I'm going to label as SSE, meaning sum squared error. Fair? Yes?
So this weight is different from the weight in the active method, right?
Yes. The activate method computes the model. A sum squared error method will compute the error of a particular hypothesis. Let me define another term here. Okay.
I think the weight is good for this case. But
Model
activate is not.
is going to be y is equal to mx plus b. I'm going to say hypothesis y is equal to, and then I'll put some matrix here and some vector there. And I'll fill these up with numbers like 2, 3, 1, 4, 2, 2. Something like that. The difference between a hypothesis and a model is a model supports lots of possible parameters, and if you pick particular parameters, then it becomes a specific model or a hypothesis. Does that sound good? At least this is the terminology that's used in one of the books that helped me learn about machine learning, so I think that's a good way to represent it. Now, we can refer to a model space or a hypothesis space, I think they use those terms interchangeably, as all possible sets of parameters that you could give to a model, right? Now, if we looked at just the model, you could call this the, there's some other spaces here. So the inputs to this model are x, and the output is y, right? And M and B are the parameters. So what if I were to say input space? What would that mean to you? It'd kind of be the set of all possible vectors of x that you could feed in, right? And how many dimensions are in x? However many there happen to be. In the housing problem, there are 13. In our unit test, there was 3. There could be any number. How many dimensions are there in y? Again, it could be arbitrary. In the housing example, there was 1. In the unit test, there was 2. Y could be as big or small as you could possibly imagine, right? So it's a vector of unspecified size. So if I were to say input space, that's going to refer to all possible values for x. If I were to say label space, what would that mean to you? Wow, I cannot type today. Label space. Would you agree that means all possible labels that go with the corresponding features? Okay, and if I say model space or hypothesis space or parameter space, now I'm talking about all possible M's and B's. And so basically any of those letters in that equation you could certainly vary, and the space of things over which you could vary them is interesting. There's another thing that'll come up called error space or error surface. And that's what I want to talk about right now. So, yes, please.
Hypothesis space are different, right? Model space would be all possible models you could have.
Yes.
Okay.
Thank you for pointing that out. Not the same. Okay. Yeah, a model would probably be all possible models, which would be things like you could have neural nets, you could have decision trees, you could have all kinds of stuff. We could call that model space. I bet you will encounter at some point somebody using the term model space to mean the space of all possible hypotheses that this model can support. So whenever you use terms, people are going to abuse them, and you need to be a little flexible with terms. So there's no one true definition for any term anywhere. Sorry. Even math. The thing that drives me nuts is whenever we study control theory, people use this symbol not to mean 3.1415, but to mean policy, because pi is the Greek letter that starts with a p, and the word policy is a function that maps between state and actions. And anyway, that's just a tangent. But the point is, no matter where you go, people will use symbols to mean something other than you want them to mean. So try to be a little flexible, but also try to learn what we use them for so you can understand what I'm saying. Is that fair? Okay. Basically, right now, what I have labeled as weights, what is this space? What is this axis? Well, it's weights, but
All possible values for the weight?
yeah, which is the same thing as the hypothesis space. What I'm trying to get at is, imagine that this one line somehow represents all the possible trained models, aka hypotheses, that could exist, are different points on this axis. Now, there's no way you can represent that on one axis, so pretend there's really a 13-dimensional space coming out of the board, and there's 13 axes here, and every point in that space is one of the possible hypotheses, right? Now, for any given model, let's arbitrarily pick that one. So I've got a hypothesis. I said model, I meant hypothesis. If I were to take that hypothesis and take some training data, and again, we have to have some training data defined. Suppose we have some training data, and I measure the sum squared error of that hypothesis against that training data, I will achieve some number, right? And let's suppose that number's right there, how about? If I go somewhere else, maybe I pick this hypothesis, and I measure its accuracy against the same data, I'll get some other number, and maybe it will be right there. And if we keep doing this for a long time, we'll eventually get some kind of a surface, right? And if we measured it completely, maybe it would make some kind of a parabola. Okay, this is what I'm going to refer to as an error surface. And the reason it's always going to be a surface is because error is a scalar, right? It's a single value, and it's never going to be a vector or a multidimensional thing. It's always going to be one number. So I can take however many weights I happen to have. Now imagine a big hyperdimensional space here, and wherever I go in that space, I can map it down to a single number, which is this sum squared error here. Do you see how that's always going to be a surface? It's always going to be however many dimensions I'm in minus 1, because I'm mapping from n dimensions down to 1 dimension. Okay. What's that?
Taking the example of 2 dimensions is easier.
It is a lot easier to imagine here, yeah. So this is 2 dimensions. Now let's go into 3 dimensions. If I extend an axis coming out of the board right here, then now I've got a 2-dimensional surface of model space, which maps to a 1-dimensional error, which means that's going to be a 3-dimensional bowl, right? Okay, well, if it works with 2-dimensional hypothesis space, then it works with 3 and 4 and 5 and 50 and 1,000 and 2 billion. So don't really know what a hyperdimensional bowl is, but we can at least use our minds to envision that there must be something like that, right? And why is it bowl-shaped? Because we squared it, and squaring something makes it bowl-shaped, and that's just the way it is. Okay? The reason I'm expecting everyone to get approximately equal sum squared error results is this. Imagine you put a marble right here, and you have a bowl, and you let the marble roll down the hill. Where's it going to end up? The optimal point, right? Imagine you start the marble up here, and you let it roll down the hill. It's going to end up in the exact same point. Basically, because the error surface, whenever you use a linear model with any data, some squared error will always form a bowl that has exactly one global optimum. And because of that, and because OLS computes that one global optimum, we should all arrive at approximately the same point. Now, the reason there will be some variance is because I might split the data when I shuffle the data, I might split it here and you might split it there. And depending on the very subtle nuances of how you write your code, I might test on 12 patterns or train on 12 patterns, then test on 6, and you might train on 13 patterns and test on 5. Something like that. So you'll get slightly different numbers. However, if we do 10-fold cross-validation and then average over 10 folds, it usually works out. And then if we do several repetitions of that, it averages out even more. So the number just the error diminishes away, and eventually we should all get approximately the same accuracy with this problem. Fair enough? Okay. That was a long-winded explanation to why we're all going to get about the same answer, but I really did it so I could throw some terms at you and recall to your memory what these things are about. Okay. Suppose we have here 3 points. What does a linear model look like in this space? And by 3 points, I mean 3-dimensional space. It's actually not a line, it's a plane. So suppose I define 3 points here. Now you can imagine a plane. What's that going to look like? Pretend that plane goes exactly through those 3 points. You're convinced, right? How's my 3D artwork going there? Okay. The equation for a hypersurface like that is y is equal to mx plus b, where m is a matrix and b is a vector. What's the size of m going to be in this particular case? Let's see. I'm going to say that we're taking 2 inputs because we have 2 x-axes on the base here, and each of those is mapping to one vertical position. So this is a 2-by-1 matrix, which is actually just a vector. Okay, suppose we take this matrix, let's do a 3-by-2 matrix because this will be, if M is a 2-by-3 matrix like this, that supposes that X is going to be a vector of size 3, right? That also supposes that B is going to be a vector of size 2. Do you agree with that? Okay, so when I compute this intermediate value, that'll be a vector of size 2, and the final answer will also be a vector of size 2. Okay, when we compute these values, we're going to take the dot product of this vector with that vector to compute this element. And then we're going to add it to just that element, and that's going to be that element of the answer. We could certainly write out that element of the answer as something like y1 is equal to m1x plus b1. Right? And the equation for the second element of the answer would be y2 is equal to m2 times x plus b2, where in this case that's dot product between these 2 vectors, right? And this is just an alternate way of expressing the same thing. These 2 equations then form the exact same thing as this one equation. It's just that m in the 2 equations is a vector, and m in this one equation is a matrix. And in fact, what is a matrix exactly? What is the meaning of a matrix? How do rows differ from columns in a matrix? Turns out it's a trick question. Matrices have no meaning It's just a bunch of numbers. And that's something that people have a hard time wrapping their head around. A matrix there's not one right way to use a matrix. It really is just a two-dimensional way of throwing out a bunch of numbers and not assigning labels to them because it's too cumbersome. That's really all a matrix is, and a vector is just a one-dimensional bunch of numbers that we're going to throw together. It doesn't have meaning until you give it meaning. And the only reason we're throwing these two equations together is because we'd rather write this than those two equations. Okay. Sorry, I am trying to build up to an answer. I just have to get out a lot of concepts because it's the start of the semester and have a lot of concepts to throw out there. Okay. But lest I lose my focus, let me read this again. Okay. If you use the exact number of points necessary to constrain your model, meaning if you have, if you're in 3 space like this and you use exactly 3 points, your model will be perfect, right? Within the precision of how accurate your machine is. And then if you recompute values based on a perfect model, you'll get nearly perfect answers again. And then when you finally measure how close the weights are, they should basically be accurate within very, very, very tiny precision. Okay? Yes?
Except for the random noise we added.
That's really the only thing that makes a difference is this random noise right there. Okay, let me back up and just give you the straight answer instead of beating around the bush. Here's the answer. Crank your noise down to 0, your accuracy should be perfect. Crank your noise up a little bit, see what happens. Your accuracy shouldn't diminish very much, meaning if you add a bunch of noise and it's still pretty darn accurate, your system's working really well. If you add just a little bit of noise and the whole thing just falls apart, it can no longer compute anything, something is a little bit fishy. Now, here's where noise starts to make a really big difference. And I want you to be able to reason about this more than I want you to know my answer. If we had 3 space and we give it only 3 points and I add a little bit of noise, meaning I grab this particular point and I raise it up a little bit, what's that going to do to my model? It's going to totally change it, right? And thus my accuracy will get a lot worse. Now imagine instead I have thousands of points, just to pick a hypothetical extreme. That was my spray paint tool, and I've plastered points all over the surface. So I have thousands of points now constraining my model, and now I inject a bunch of noise. What will happen? Some of the points will go up, some of the points will go down. On the average, the model will go right through the center of them, and therefore, when I recompute my original model, basically it should be dead on accurate, right? So if you have a lot of training points, you should be really, really accurate no matter how much noise you add. If you have a very tiny number of training points, a little noise is going to throw those off, which is going to throw your model off, and you should get a lot.